both, it's kind of like once you're used to it, everything's fine. You know what I mean? So it's like, it's not like anything is like broken, but it is confusing to students sometimes that when we say tan inverse of x, we're talking about the inverse function of tangent, not the multiplicative inverse of tangent, but they're both written the same way. Yeah, not the best notation ever made, but once you're used to it, everything's fine.
Okay.
Yeah.
So if we were to write tangent of x to the negative first power,
yes,
that would be,
yes, that would be the multiply. So if we wrote this tan of x to the negative 1, then yes, that would be 1 over tangent of x. But it just so happens that we almost like found a way to avoid this completely because we have something that we write instead of this.
Right. Yeah.
Cotangent of x. Cotangent is the multiplicative inverse of tangent. And so it is in that sense, we would never write this. So it is clear, but it still is tricky. So good question. I could talk all day about function theory and multiplicative inverses and stuff. That's kind of my happy place, but we won't. Okay, yeah, one of the classes that I teach here is called Algebraic Structures. And we just learn about in algebraic structures, like, but the way that I like to describe algebraic structures to people that's kind of fun is if aliens did math, it could be the same as us, or it could be something totally different. But there are certain rules that we can figure out that all mathematics has to follow, not just ours. Ours, we typically are using the real numbers. So when you learned algebra, you learned algebra of the real numbers. And so, but what if somebody invented some other algebra? Could you tell me anything about the aliens' math? Now, you couldn't tell me everything because you wouldn't know their numbers, you wouldn't know how they multiply, you wouldn't know how they add, all of that stuff. But would you know anything? And in algebraic structure, we kind of figure out in any mathematical algebra system, what can we say is true? And that's kind of what algebraic structures is all about, like the structure of an algebra. Not the algebra we work with, which is the algebra of the reals, but the structure of all algebras. So it's interesting. Fun times. Anyway, that's not what we're here to talk about today. Today we're here to talk about improper integrals. Yes, sir.
So can you not evaluate from like 0 to infinity? It has to be the limit of a to infinity from the, because I feel like it's the
same
thing.
Yeah.
It's just like 2 extra steps you have to do.
Yeah, good. Okay, so this is worth talking about since I don't know if I necessarily talked about this on any of the videos, maybe I did, but why do we have to do the limit thing? Seems like a pain. Like what's a really easy example here? Let me just take like the most simple thing, like integral 3 to infinity dx over x squared. So let's just take the very first problem in the book, 3 to infinity dx over x squared. Okay, and somebody might say, come on, like just leave the infinity in and everything's fine. And so let's see, right? So what's the antiderivative of x to the negative 2? I suppose it's minus x to the minus 1. So I'd say minus x to the negative 1 evaluated from 3 to infinity, okay? And then I'd say, okay, now plug it in and I get negative x to the infinity to the negative 1, which is actually 1 over infinity, minus, then I plug in 3 and I get minus 1/3. Is that correct? So what's 1 over infinity? Okay, agreed. It is 0-ish. Well, first of all, there's no such thing as infinity, at least not in this class. So what do you mean 1 over infinity? I have no idea what you're talking about. So explain it to me.
A very, 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 very big number.
Okay, that's not infinity.
It's approaching 0.
Oh, wait, you said approaching. What are you talking about?
It's getting infinite close to 0.
Yeah, but it's not 0.
Yeah.
But it is 0. So this is like the ancients of mathematics and like the great thinkers of math, like Newton and all of these guys. What they discovered is that there's 2 types of infinity. There's what we could call potential infinity, and there's what we could call actual infinity. What we deal with all the time in calculus is what we would call potential infinity, because it's like infinity's not a number. Infinity is an idea. Does that make sense? Because what I'm just saying is like, come on, get really, really big. Go all the way out there. But it's like, is there a number out there? No, there's no number out there beyond all the numbers. But if there were, let's call it infinity. So it's kind of like, just keep on integrating. Well, here's the deal. So 1 over infinity, I'm just going off on this, but it's kind of like, there's no, what do you mean 1 over infinity? 1 over idea? It's like, no, it's not really 1 over idea. It's 1 over really big number, as big as you want. But as soon as I say as big as you want, 1 over as big as I want is as small as I want. So it might as well be 0. Because any number I choose, I could get it smaller. Right? If I said 0.1, could I make this number big enough so that this is smaller than 0.1? Yes, and I could make it as small as I want. So this is technically 0 in the limit, but not in reality. There's no infinity that I divide by 1 by. I divide it by a really big number. Yeah.
Okay, so potential infinity and what was the other one you said?
Actual infinity.
Okay, so what you're saying is that when we're using actual infinity, because that doesn't exist, you can't evaluate 1 over actual infinity.
Okay, let me be clear. I'm not saying that actual infinity doesn't exist. I'm saying it doesn't exist in this class.
Okay.
It's kind of funny because like, have you ever noticed this all through your career of mathematics? Everybody just lies to you all the time.
Yes.
Okay, so first you're a little kid and you're learning how to add and stuff, and one day you're maybe a really clever student, and you say to your teacher, well, what, and you're learning subtraction, and you say, what if you took 2 minus 3? And the teacher's kind of like, well, you can't really do that. It's like, okay, until later they say, well, yeah, you actually can do that, and it's -1. And you're like, what's up? You told me you couldn't do that. And then it's kind of like, what happens next? You get to a point where you're doing square roots, and then you get like the square root of -3, and you say, what's the square root of -3? It's like, that's not a real thing. It doesn't exist. Until later they say, well, actually it does exist, and it's like, square root of 3 times I, right? And it's like, oh, okay. And this just keeps happening through your mathematical career. So I'm not going to lie to you. There is a such thing as actual infinity, just not in this class.
So we can't evaluate that.
No, it's not a number. That's the problem. There is a such thing. Well, it is a number, but it's not. It's what we would call a transfinite number. And so we can't evaluate like 1 over that number, but we could evaluate 1 over any very, very big number, and it doesn't matter how big. So in the limit, everything's fine.
So the problem is that's not saying the same thing. The limit and this are not this, like 1 over infinity and limit as b approaches infinity 1 over b. Those are not the same thing.
That is correct.
And that's
But then back to your question, functionally, can I do it?
Yeah.
Okay, kind of. So let's just do this. So 1 over infinity, we're like just suspending belief, and we're just like, it's 0. And I'm like, okay. And then we say minus a third is a third. And then the question is that what I would have gotten anyway? If I did the limit way. In this problem, yes. Okay. When would it be wrong, potentially? Could it ever be wrong? Excuse me. Could it ever be that when I just use infinity and don't do the limit as like b goes to infinity of yada, 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 could it ever be wrong? Yes, if you have to use L'Hopital's rule. So it is possible that you could get a situation where you are plugging in infinity to something like x squared minus x over x cubed minus 2. And you need to plug in infinity. And guess what? That's bad. Because now you've got infinity minus infinity over infinity minus 2. And you're kind of like, now wait a second, that's not 0. Well, actually, it is 0 in this case. But why is it 0? Is it clear right now that if I plugged in infinity to this thing, I should get 0? Only if I'm taking a limit.
Yeah.
If I'm just plugging in infinity, I get infinity minus infinity. Well, right off the bat, infinity minus infinity, if you remember your L'Hopital's rule, that's an indeterminate form. So we don't know what infinity minus infinity is. Agreed? And so now this is just a big mess. So if you get into a case, and there are some problems like this in the book, where you get into a L'Hopital's rule situation, you can make a mistake. So the limit helps you because you remember, oh, I'm taking a limit as x goes to infinity of like an infinity over infinity situation. Limit as x goes to infinity of infinity over infinity. I use L'Hopital's rule. Does that make sense?
Yeah.
If L'Hopital's rule just happens to not come up, this works. And in fact, if I'm just kind of doing one of these on the fly, I usually just hold the infinity in there, just like I did here, when I'm just actually doing it. And then I do this, and I would have gotten a third, and it would have been right. But I realize that I can get myself into a mess. And so I just have to be careful. So practically, if you're doing an integral like this, this is okay. Just be careful. On the exam, it's not okay. You need to show me that you actually know what to do. The idea, here's another thing though. I know you asked a simple question and I'm going off, but it's your fault. No, so here's the thing. Here's another piece. What is an integral? Okay. So remember, when we first learned about, this is at least the way we're writing this right now, it's a definite integral. Typically, definite integrals are from A to B, correct? And then we ask how much area is there under the curve between A and B. Now, how do we actually do that? We chop it up into what, typically? Rectangles. Okay, so what, and how many rectangles do I chop it up into? Please, don't say the wrong word, please. A lot. Not what? Not infinity. Why not infinity? This is actually really, really important when we're having this discussion of like writing an infinity right here.
Then there would be 0.
Yeah, if I chop this up into infinite rectangles, then what would be the width of every rectangle? 0. What's the area of a rectangle with width 0? 0. So if I add them all up, I get 0 area, and that seems bad. Would you agree? So one of the reasons, actually, an integral itself is a limit. Do you remember it? There's like, this is the Riemann sum, and you take the limit of a Riemann sum, and then we define that as the definite integral. Okay. So we do that between A and B. And so what I'd like to say is we don't divide it up into infinite pieces. We divide it up into n pieces. and then let n get big. How big? Well, as big as you want, but not infinite, because that would make all of them have width 0, which is no good. So we have to divide it up into n pieces. So I chop it up into some pieces, draw some rectangles, add up the rectangles, right? And then if I want to get more accurate, I let the number of rectangles get big, and in the limit, I get an integral. Okay, so what changes in this situation when I add the infinity? Well, instead of going from A to B, now I'm going from like A out to infinity. And so maybe I have something like this, and now I want all of that area, right? All the way out. Okay, so let's go through our same little song and dance. How many rectangles should I cut this into? Huh? I don't know what you're talking about. What's infinity? Okay, that's not infinity though, but I'm with you. How about a really big number? Well, okay, let's do that. How about 100's not a big number, but let's pretend 100's a big number. So I want to cut all of that length, which is quite a bit, into 100 pieces. How big is each piece? Oops. Infinite. Agreed? That seems bad. Like that each rectangle has infinite width. So right off the bat, it's like, okay, take all of that length, which is infinite, and then divide it into 100 pieces. It's like, yeah, no good. You can't do it. Is everybody with me? So it's like, you cannot do it. Like this is a shorthand version for something else that is a limit, right? The way that we would write this, as you know, since you've been working on the homework, is we'd say this is like the limit as b goes to infinity of the integral 3 to b dx over x squared. And it's kind of like, and it rightfully so as a student, you're like, come on, man, this feels like a drag. Like you're making me write all these extra symbols, and I just don't like writing extra letters and numbers when I don't have to. And so why do we do it this way and not just the way I just did it up here? It gets you the right answer. The reason is so that you actually understand what's happening. And that is that I cannot do this, because as soon as I start chopping into rectangles, I have a big problem, because I just chopped it up into infinite rectangles. Does that make sense? And that's no good, because each of the, well, first of all, I can't chop it up into infinite rectangles. Second of all, I can't even chop it up into 100. I can't do anything with that. But here's what I can do. I can say, okay, what if I then, instead of chopping it, let's let this be 3, just because that's what we're doing right now. Right, and then I say, let's chop this off and just cut all that nonsense away. And we'll say, let's call that B. And now what if I wanted to just integrate from 3 to B? Is that legal? Does everybody agree that it is legal? Yeah, that's what we've been doing all the time. And then what I'll do is I'll just take B and start dragging it. And is it ever illegal when I move B? It's legal here, it's legal here, it's legal here, it's legal here. It's legal as far as I want to go. But it's illegal as soon as I hit what we would call infinity.
Because you can't actually go there.
You cannot get all the way there and still cut it up into a finite amount of pieces. So what I can do is say, let's just go part way there, cut that up. I could integrate that, or I could integrate it here, or here, or here. But what I'm going to do is I'm going to say, so integrate it to generic point B, and then let B get big. That's legal. So it's a limit, because I cannot do it. I mean, there's no such thing as an integral to infinity. There's just an integral to a very, very, very big number, and then see if it's getting close to something as the big number gets bigger. Does that make sense? Okay, so that was a very, very long answer to that question. But I actually think it's super important because it does seem like a waste that we do this instead of this at times, other than L'Hopital's rule that can really mess you up. But this is really, really actually the reason why we have to do it is because there's no such thing as an integral from 3 to infinity. That's impossible. But we can still figure out if we could do that, if we could go from 3 to infinity, what would it be? That's kind of the miracle of calculus in some ways is like, this should be impossible, but we can do it anyway using another limit. When you think about an integral as a limit itself, this is actually the limit of a limit. Right?
Yeah.
So it's pretty cool stuff if you really start to dig in and think about what's going on. Yeah.
So nobody who's a competent mathematician would write in an integral from infinity to 3. They always write limit of b to infinity b to 3. If they're not trying to test you, you know it. They
Oh, like nobody would write this, they would write this.
Yeah.
Well, you do write this. Actually, the competent mathematicians would all write this, and they might even do this, but they know.
They know why.
They know what's going on behind the scenes. So in their head, this is happening because they understand that this isn't a real thing. This is a limit as this number gets big because there's no infinity to integrate to. Now, I could go off on this. Actually, the course I'm teaching right now, one of my upper division courses, is called Real Analysis. And real analysis is where we prove calculus. So we're doing all the proofs behind calculus. So this is the kind of stuff we just talk about every day, what I'm talking about right now. This is like, but here, let me show you something else because now you've got me started. Okay, again, your fault, not mine. Okay, so here's a question for you, and this is very fun. Let's say I have a function, and I have this point 1. And I say, how much area is there over the point 1? Just over this one single point. How much area is there? Yeah, you can be confident. It is 0. Why? Because what's the width of that little dotted line? 0. And then it does have height. But would everybody buy my story if I said there's no area over that one little point? Does everybody buy it? Please do. It's true. Okay, there's no area over that point. What if I went over here to the point 2 and I said, how much area is there over 1 and over 2? Yeah, it's 0 here and it's 0 here. So 0. There's no area over those 2 points. Okay, I'll add in 3. It's a bummer, still 0. Let's add in all of the counting numbers. 3, 4, 5, 6, 7, 8. We'll add them all. How much area is over all of those? 0. 0 plus 0 plus 0 plus 0. Still 0. Okay, now let's just go ahead and add in all the halves. How much? 0. Okay, all the thirds. Still 0. The fourths, the fifths, the sixths, all the fractions. All the fractions. How many fractions are there between 0 and 1? Infinite. So there are infinite points in here that are fractions. They're all over the place in there. And how much area if I added those in? So every fraction in the line, how much area is over those points? 0. And then you start to say, what's going on here? Because how much area is there between, like, let's say 1 and 2? Well, not much. We could evaluate it, right? We know how to do calculus. There is area. How much of that area is sitting over the rational numbers? 0. So where's it sitting?
So wait, we can take a limit here and say it equals 0 based upon our idea that we're doing, maybe.
Maybe.
It's like if we take like limit as like, because we've done a certain amount of times, and then I don't know. It's like you have n and it's growing the amount of n's you have. It's like a sum.
Well, the crazy thing is, like, over the rational numbers, which are the fractions, there is no area. And so where does all the area live? Well, it must be over the other numbers. And what are the other numbers? The irrationals. So in some sense, the number of irrationals that are in the real line far outweigh the number of rational numbers. And actually, when I describe this to people, I tell them that, like, imagine that the ocean is the irrational numbers. All the irrational numbers are in the ocean. Then if you described the rational numbers as a drop of water, you would be giving too much credit to the rationals. There's so much more irrational numbers than there are rational numbers that we can't even comprehend. But then you're kind of like, but wait a second here, they're all over the place. Like, if I take any little open interval, are there rational numbers inside? In fact, that's a proof I did just the other day in real analysis, that in any open interval, there is a rational number. So in between any two numbers, there's a rational number. And in between any two numbers, there's an irrational number. But the irrationals far, far outweigh the rationals. The way I like to describe this is, imagine that the rationals were food color. And have you ever like had like a bowl of water or something, and then you just do a drop of food coloring and then you mix it up? What happens to the water? It like turns pink, right? And so in some sense, it's like, well, that little drop just went all the way through the water. So if you took any spoonful of that water, there's red in it. But does that mean there's as much red in the water as there is water? Not even close. So what's going on is we're taking the rational numbers are like one little drop of food coloring in the irrationals. And so the irrationals are the whole line, basically. Here's another way to think about it. If you know lottery machines where you kind of like roll the lottery balls and then you reach in and you pull out a ball. Let's say you took all the real numbers and you dumped them into a lottery ball machine, the rationals and the irrationals. You reach in your hand, you pull out a ball. What's the probability that you got a rational number? 0. Is it possible that you got a rational number? Yes. So this shows us that there is a such thing as having a probability 0, but it's possible to happen. So just because something has probability 0 doesn't mean it can't happen. Here's another way of thinking about that that's similar. Let's say we have an intersection right out here, like North and that's not Villa, that's Meridian. So we're out here at North and Meridian. What's the probability that when this goes around, and this is straight up, let's say 2 o'clock, it's straight up 2 o'clock to the instant. What's the probability that there's a car accident out on that intersection? On that instant, not in the minute, on the instant. 0. There's 0 probability of that. It will happen at an instant, But what's the probability that it's straight up 2 o'clock? 0. Could it happen at straight up 2 o'clock? Yeah, it's the same thing. This is called continuous probability. And probability is all based on calculus. Okay, so it's kind of like, except discrete probability, which is like, it's interesting, but it's a different subject. So people think I understand discrete probability, like if I roll a die, what's the probability that I get a 1? 1 in 6, it's like, hooray, you understand discrete probability. That's not the probability of the world we live in, unfortunately, which is continuous. So if you want to understand probability thinking in our world, you have to understand calculus and the nature of the real numbers. Anyway, fun times. So all that to say, this is like, we do these things in calculus and we compute something. This is very simple, right? Like I start with this, I do some things. How much depth is there to this line? It's like ridiculous. Now it's such an easy computation, but here I'm taking the limit of in rectangles that I'm taking to infinity, but then as I'm doing it, I'm taking the interval itself to infinity. All of that's happening at the same time when I write this 1/3. And it's kind of like, and all of that is lying on the fact that this is all happening over the irrational numbers, that really the rational numbers don't really matter at all in this game. And there's just some craziness. By the way, how many rational numbers are there?
We say infinite.
It's okay, infinite. I agree with you. There are infinite of them. Even the natural numbers, I mean, what I mean by the natural numbers are 1, 2, 3, the counting numbers. How many counting numbers are there? Infinite, right? But here's the thing, that didn't I say that there were more irrationals than rationals?
Infinite squared.
No, we can't think of that.
So can you have bigger infinity than infinity? Yes, you can. There are different sizes of infinity. And so when somebody says 1 over infinity, that's nonsense. What are you talking about? What's infinity? There are different sizes of infinity. And in fact, it would be very, not easy, but I could prove to you that there are infinite sizes of infinity. That if you give me any size of infinity, I can find you a size of infinity that's bigger. It kind of, and so think about that for a second. There is no biggest size of infinity. I think up to this point, pretty much people think, come on, man, infinity's infinity's infinity. I'm sorry. It's like, well, no, it's not, because here's infinite points and they have 0 area over them. It's like, so how many more do I have to add to get some area? Well, a lot. A lot. Even if I doubled the number of rationals in the line, that's not good enough. Anyway, so these are good questions. Like, so the question you had was actually like super, super good, because it kind of questions like, why can't I just do something simple, like just do this computation? And it's like, well, in general, you kind of can, but there's so much like depth to what's happening while we do these computations that we just like totally forget. It's like, you just do some stuff and you get a 1/3 and life is wonderful. It's like, well, how did we get here? Like, we had to first just be able to go from A to B, and then we've got to pull B out to infinity, and we've got to do all this stuff, and we've got to understand the structure of the real line, and there's just so much there. So if this kind of stuff, like this little talk I'm giving right now, that I wasn't planning on giving, by the way, if this kind of stuff is interesting to you, that's what a math major does. I think a lot of people kind of think, I bet that math majors learn how to do really hard integrals. It's like, no. Math has nothing to do with integration. In fact, I often tell people that the only math class you've ever taken and it's kind of like a scratch on math. The surface of math is you took geometry. Geometry is the only class that I would say is a math class. And then you're like, well, what's all this stuff I've been taking then? Like algebra 1, algebra 2, pre-algebra, trigonometry, pre-calculus. What's all that then? It's like, that's called arithmetic. Like you're just learning how to move symbols around. You're learning what a function is. You're learning what all these things are. You aren't doing any math. Math is proving things. It's proving theorems. Okay, so you're saying, here's a proposition. We can either prove it's true, we can prove it's false, or maybe we can't prove it at all. But yeah, that's the question. Like when this was discovered that there were bigger sizes of infinity, people didn't like it very much. Okay, a guy named Cantor actually came up with this idea that there are bigger sizes of infinity, and he came up with a hypothesis that's very, very, very famous in mathematics, and it's called the Continuum Hypothesis. And the Continuum Hypothesis was, he said, okay, the size of the counting numbers, 1, 2, 3, 4, 5, forever, that's infinite. And I'm going to call that the smallest size of infinity. And then he said, and then there's the size of the real numbers, which is much bigger than the size of the counting numbers. And we'll call that the second biggest size of infinity. He couldn't prove that. So basically he's saying there's this size of infinity that's the counting numbers. There's this size of infinity that's the real numbers. Could there be a size of infinity that's in between? It's bigger than this one, but not as big as this one. He said, no, this is the second biggest size. That's called the Continuum Hypothesis. He spent the rest of his life trying to prove the Continuum Hypothesis, actually died in a mental institution. He spent his whole life trying to figure out, are there sizes of infinity in between the two? He was able to prove that there are bigger ones. He just couldn't say that there were or were not sizes of infinity in between. So these are the types of like conversations when you get into like more theoretical mathematics. This is what mathematicians think about, is like, what is the nature of infinity? So it's very easy for us to write something like 1 over infinity. It's like, that is such a loaded thing to write on a board that I can't even tell you. Like 1 over infinity, well, there's so much there. But when we say it's just potential infinity, like really, really big, everything's fine. It's when we say it's not just really, really big, it is the size of infinity. It's like, okay, now we're talking something really, really deep. So if you've ever wondered, would I like math or like a math major or something? You shouldn't think like, do I like to compute hard integrals? That's not what math is. Math is about investigating the world that is around us mathematically and proving that things are true or aren't true or yada, yada, yada. So anyway, fun times. I didn't answer any questions. Yes.
Is that real analysis class? Is that like grad level class?
No, it's undergrad. Yeah, it's like a junior, senior undergrad course.
Is that like 230 or 300?
It's like 421. Yeah. But to take that class, you have to take a different class. And how many of you are engineering majors? Yeah. Do you guys know that to get a math minor as an engineering major, you have to take one more class? Intro to Proofs. And Intro to Proofs, you got to take that class before you take real analysis. Because in Intro to Proofs, we talk about like, what is a proof? How do you write a proof? What are techniques for writing proofs? All of this like common vernacular and like language that we need to actually do cool stuff. So if you're interested in that kind of thing, I actually am teaching Intro to Proofs next semester. It's the greatest. Okay, so like calculus is good, but like when you start getting into proofs, it's kind of like that's where it gets exciting, and you get to start doing learning some really cool stuff about math, like about sizes of infinity and different things like that. So anyway, that's my quick advertisement for math. Yeah,
Can we do number 8?
sure. Why not? Seems so anticlimactic, but we'll do it. I wonder if anybody's actually watching this video and it's like, what happened?
I think so.
Okay, so somebody said 8. Is that right?
Yeah.
Okay, so we've got the integral from 2 to infinity. Oops. 2 to infinity. Of dx over x. All right, so what we want to do here is first let's convert it into its limit form. And like I said, do we technically have to do it? Maybe, maybe not. I don't know if I'm going to get a L'Hopital's rule problem typically when I start. But so let's assume, and for the purposes of our exam, we need to convert it. So we need to write this as a limit as b goes to infinity of the integral from 2 to b of dx over x. Now I've got a nice definite integral, and I know what to do with that. I can take its antiderivative, so I get limit b goes to infinity. Antiderivative of 1 over x is just ln of absolute value of x evaluated from 2 to b. So now I can plug it in. Still have the limit hanging out. And you really just kind of let the limit hang out until you're all done, and then take the limit. So it's kind of like there are 2 problems. First, you're just finding this integral. Get it all the way done, and then take the limit. Don't start messing with the limit before you're done taking the definite integral. So now we plug things in, and we get ln of absolute value of b minus ln of absolute value of 2. So now we take the limit. So we let b go to infinity, and we get the natural log of not infinity, but a really, really big number. So what's the natural log of a really big number? A really big number. So in some sense, this is going to infinity. So we get like infinity, and this is just minus ln of absolute value of 2. But subtracting just a little bit from infinity isn't doing anything. So this is infinity. And now we would say that this integral diverges. Okay, so what does it mean to diverge? It just means it doesn't go to a number. Okay, so there's different types of divergence. This is the type of divergence where it actually is very, very big. So if we calculated the area under this curve between 2 and infinity, it's a huge amount of area, infinitely big. So it diverges to infinity. But we could also get something where it's kind of like it's just not going anywhere. And that also diverges. Yeah.
Like tangent gets really, really close to, well, it's like there's some sign trigonometric functions that like they just don't actually approach anything. They oscillate.
Uh-huh.
But
Did
that's
I
their version of it.
Did I do one of, have most of you watched the video? Did I talk about Gabriel's horn? Oh, sad story. Okay, I don't want to ruin it. It's so good. I'm not going to talk about it today. I'll talk about it on Friday. But remind me to show you Gabriel's horn on Friday because it's like one of my favorite math problems ever. Question? Yeah.
I was wondering if you could quickly do number 28.
28. Let's look at it. I think I can quickly do it, actually. Trying to find a good pen here, sorry. So 28, better. We have integral from 1 to infinity of tan inverse of s over s squared plus 1 ds. So first let's write it as a limit, as we should. So we could rewrite this as the limit as b goes to infinity of the integral from 1 to b of tan inverse of s over 1, oh, I'm sorry, s squared plus 1 ds. Okay, and now I'm going to do something kind of clever. I'm going to say, what if I did a U-substitution and U was tan inverse of s? What would the derivative of U be? What's du? Yeah, it would be 1 over s squared plus 1 ds, which is everything else, correct? So I could rewrite as this is the limit as b goes to infinity of integral, I'll deal with this in a second, of u du. But now I should change, either I need to move back to the old limit someday, or I should change my limits. Either way is fine. If s is 1, what's tan inverse of 1? Pi over 4, yeah. So this would turn into pi over 4. And then if s is b, tan inverse of b is, I suppose, tan inverse of b. And we can deal with that later. Okay, so now I take the antiderivative of u, and I still have limit. As b goes to infinity, just deal with that later, of u squared over 2, evaluated from pi over 4, to tan inverse of b. So let's plug it in, and I get limit as b goes to infinity. That just hangs out. And then I plug in the tan inverse b, so I get tan inverse of b, quantity squared, divided by 2, minus pi over 4, quantity squared over 2. Now we can plug in b going to infinity. So what's tan inverse of a big, big number? So what does tan inverse get close to as b gets really big? Pi over 2. So this is just pi over 2. So this is equal to pi over 2 squared over 2 minus pi over 4 squared over 2. And now we just need to do a little bit of work here, right? So this is pi squared over 4 divided by 2 minus pi squared over 16 over 2. And we could combine those, right? What would we get? We could write this as 4 pi squared over 16 if we wanted to. So I have 4 pi squared over 16 minus pi squared over 16. I suppose that's 3 pi squared over 16 over 2, or this would be 3 pi squared over 32. Sound good? Okay, I'm over time. But that's it for today. Hopefully you enjoyed your mini real math lesson, and I'll see everybody on Friday. That's funny.